Today I'm going to talk about LeetCode question number 300, longest increase in subsequence. So given an integer array nums, return the length of the longest strictly increasing subsequence. So strictly increasing cannot be equal. There cannot be any equality in the subsequence. A subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. For example, 367 is a subsequence of this array. So the order is preserved basically. 3, which comes 6, which comes 2, which comes 4, 7. Okay? So how do we go about this? Well, you might think we could go through the array one by one. So start from here, iterate through the rest of the array. If there are any strictly increasing subsequences, then we add that to the total. Okay. But this won't work actually, because let me show an example. Like I'm using my own example here. Okay. So for example here, if we start here and then iterate through the rest of the array to find strictly increasing subsequences, we have 9 here. Okay, great. And we move on. This is smaller than 9. This is smaller than 9. So we see that the count is 2. But actually, the longest increase in subsequence size is actually 3, because we have 4, 7, and 8. Okay, so we have a decision to make. Basically, so if we start at 4, we see 9, which is larger than 4, okay. When we see 7, which is larger than 4, we kind of have a choice to make here. And this is where our decision tree kind of comes in. 4, 9, 7, 8, okay. So if we have a decision tree here, okay, we could start at 4, and from 4, we can go to 9 or 7. Okay, from 9 we can't go anywhere. From 7 we can actually go to 8 here. Okay, and what if we start at 9? Well, from 9 we can't go anywhere. From 7 we can go to 8, and from 8 we actually can't go anywhere here. Okay, so this is what our decision tree looks like here. We have to start off, you know, at each element here. Each element has to be our starting point here, because if you have like 10, 1, 2, obviously this longest increasing subsequences of size 2, there's an option of not starting from the beginning. So yeah, this is what the decision tree looks like. Calculating this can take exponential time, but we can notice a pattern here. Okay, notice how when we calculate, you know, what elements come next, we already calculated them really. So for example, 4, you go to 9, and after 9 there's no other larger element than 9. With 4, you go to 7, and then one larger than 7 is 8, and then there's nothing after 8 that can be larger than it. Okay, and then again here, if we start at 9, we see that again nothing after 9, and if we start at 7, we see again larger than 7 is 8, and with 8 it stops here. So basically with these, we already calculated them here. So why not be able to reuse these calculations in our decision tree here? Okay. And how can we do that? Well, we can do that with dynamic programming. Okay. So how can we do this? Well, it'd be beneficial to start from the end here. Okay, and we will go bottom up dynamic programming, through dynamic programming bottom up. So we calculate the subproblem starting from the end, okay, and then from that, after we solve that subproblem, we use that subproblem to solve other subproblems, okay. So what we're going to basically do is have a dynamic programming array where it's going to be of size nums here. Okay, and initially each value is going to be of 1 because the longest increasing subsequence of itself is 1. Okay, so then what we want to do is start backwards from 8. Okay, we look forwards and see beyond 8, are there any elements larger than 8? Not equal to or larger, just larger. Okay, remember it's strictly increase in subsequence. If there are, then we can add that to our total count here. Okay, so for example, if we have like 10, this would, and then 10 would be 1, obviously. So it would be this plus 1 would go here, and we want to find the max, so it would be the max of itself, and then I guess dpi plus 1 if dpi is larger than this 8 here. Okay, so I'm going to erase this and go back to my original example here. Okay, so obviously nothing is beyond 8, so this will stay at 1. With 7, okay, we iterate the 2 elements beyond 7, see if there's any larger than it, and then we take the larger of itself and dp of I plus 1 if dpi is greater than what we're looking at. Okay, we see 8 here, so we're going to take the maximum of 1 and 1 plus 1, which is going to be 2. Okay, so now the longest increase in subsequence we have now is of length 2. What about 9? Okay, let's look beyond 7 greater than 9, nope. 8 greater than 9, nope. So we leave it at 1 here. And what about 4? So we look beyond 4. Is 7 greater than 4? Yes, it is. So we didn't take the max of itself, which is 1, and then the 2 plus 1, which equals to 3. So this will now be 3. And then we also find 8 here. So again, we use this formula, take the max of itself, and then it's solve problem plus 1, which is equate to 2. 2 is smaller than what we currently have 3, so we'll stick to 3. Now, obviously, what we can see here is we have 3 as our answer. And this is what we're going to do. And the runtime complexity of this is O of n squared. Just because we're basically kind of iterating through the array here. We're doing a nested loop here to look at elements further beyond the target element to element we're looking at. So now to code this up, so what I'm going to do is define my dp array first. And it's going to be the length of nums, and 1 is going to represent that for each element, longest increasing subsequence would be basically itself, which is of length 1. Okay. And yeah, so now what I'm basically going to do is iterate backwards. So I equals nums minus 1. So while I is greater than or equal to 0, I'm going to have from j is going to be equal to I plus 1, and while for actually what's better is for j in range I plus 1 all the way to nums. So if we had like this array here, I would initially be at the last point here, and then for in range I plus 1 all the way to n. In this case there's nothing else at the end, but if I was here, I would want to start here and go all the way to the end. Okay. If nums at j is greater than nums at I, then what I'm going to do is dp at I is going to equal to the max of itself, or 1 plus dp at j. Now dp at j would already be the solved subproblem of the largest subsequence at j here. So again, if I bring back this array here, so if we were at I here, if I was here, I would want to do, if I look beyond, I would do this guy's dpj plus 1, maximum of this guy's dpi, and then this guy's dpj plus 1, maximum of this guy here. Okay. And yeah, that's kind of pretty much it here. Pretty short. And what I want to return is the max of dp. So the maximum value in dp array here. Okay. So yeah, that's pretty much it there. So I'm gonna try to take it for a test run. Oh, one thing I forgot to do is decrement I. Okay, and I'll try some other test cases here. Cool, and I'll submit. Okay, awesome. Thanks for watching.